Hi, this video is about gamma, a Minkowski Spacetime Diagram Generator, an application that I wrote. The goals of gamma are to generate most of the spacetime diagrams that I've seen. It can be used as a teaching and a learning tool, and it could be useful for creating diagrams for physics papers and books. I don't know if that will be a major use of the program, but I think mostly it's a teaching and learning tool. In this video, I'll demonstrate some of the basic features of gamma. I'll walk through a few more complex examples showing how it might be used. And I'll demonstrate how to create some simple diagrams. Okay, let's step through the features of gamma. This is a sample diagram, and the user interface on this side is part of the diagram itself, so a different diagram will have a different user interface. So I can show the axes corresponding to an observer. In this case, an observer is in the rest frame, or is relative to the rest frame. We can turn on a grid for that. We can add a second observer moving at a different velocity. And I can actually, through the user interface, I can control that velocity, make it whatever I want, negative or positive. I can have the grid for that, second observer or second inertial frame. I can set up an actual world line for a third observer that has some acceleration. Let's zoom in. So I set it up so the acceleration is 1g acceleration for 2 years. So right up to that point. And then minus 1g for 2 years, so up to that point. So there's the world line for that. I can add axes labels, automatic. I can add little arrows if I want. I can add a hypergrid. And it automatically adjusts if it gets too crowded, it'll kind of step back and not let it get so crowded. I can add events at particular locations. And I can label those, so those are the coordinate points. I can boost the events, and I'm boosting it to the inertial frame of the second observer. So this one. So let's turn on their axis. Let's see, second observer's grid. And let's look at that. So here we have point 1020. And looking at, let's put on the axes. Okay, so that's 1020 right there. So we boosted that from this frame to this frame. Let's remove that. We can have lines. They're general purpose lines. They can be any angle you want. They can be set up to be parallel to some axis relative to some inertial frame. There's various ways to define them. Here I've called them light lines because they're at 45 degrees. I can intersect those with world lines and find out where the intersection occurs, things like that. You can also add a path, which could be just to diagram some particular thing, some region of the diagram. You can close the path, fill it, just have the fill of the stroke. And as you can see, I can also outline it in I chose a dotted pattern. It can also have a dash pattern. And we can have a label, just a generic label. You can put it wherever you want and rotate it. Okay, those are the basic features which you use to create any diagram. This is a more complicated example. It's an actual specific problem, which is the twins paradox. So let's look at what we have set up. So we're actually, the twins are named Bob and Alice. Bob is going to show up as blue and Alice is red. They both start out on Earth at time 0. Then Alice flies off at 80% the speed of light for 4 light years. She then turns around and comes back at the same rate. So let's see what that looks like from Bob's point of view. So there's Alice, the red dot, and she moves away, and then she moves back. And that's it. Okay, now let's look at the same thing from Alice's point of view. So what Alice sees is Bob moving away and then moving back. So it looks the same to each of them. The other one moves away and then back. Now the basic, the first postulate of special relativity is that physics works the same in all inertial frames. And the second postulate is that the speed of light is constant for all observers. And if the speed of light is constant, Einstein figured out that that everyone who is moving at a velocity other than yours will have their clock running slower. So if we go back to the first case and start it up. So as Alice moves away and moves back, her clock should be running slower compared to Bob's. And that's fine. Now from Alice's point of view, she also sees Bob's clock running slower relative to hers. And so when they meet back, they should both be younger. They should both be younger or older than the other. And so there's the paradox. I'm not going to go too much into explaining the paradox. The solution is that Alice actually is not staying in the same inertial frame, so the rules are consistent within an inertial frame, but not within 2 inertial frames. So she's in 2 different frames at different times. So the rules apply within each frame. The rules apply, but not in the whole situation. But let me show you. So what I was demonstrating was that I've drawn something that doesn't look much like a Minkowski Spacetime Diagram. It's just dots moving, but it really is the diagram, and I'll show how that comes to be by turning on the axes. Okay, let's go back to Bob's viewpoint, Bob's axis, Bob's grid, and we'll start off the problem. Let's also draw the world lines. And so you see how I translated I basically captured the motion by turning the motion into a spatial dimension using kind of the same principles as a seismograph needle or an EKG. And so it left the trace behind. So it makes it easy to see how these space-time diagrams, what they mean. This is a trace of what happened. So normally you would just see the final diagram and just the world lines for what happened. You wouldn't see it animated. So we can turn off this one dimensional. We'll just see it the way it normally would be drawn without the axes moving. Okay, now to see that Alice is in two different frames, we can display her axes. Let's go back to the beginning, and we see that her axes are already tilted. So to start, so she's going at one velocity, and now she's changing her frame of reference. Now, let's go back to the beginning. Let's turn off her axes for the moment, and we'll draw the line of simultaneity. So line of simultaneity is the set of all points in space that have the same time coordinate as some particular observer from that observer's point of view. So let's look and see, let's run this from Bob's viewpoint. And so the cyan line shows what Bob considers to be simultaneous events. And we can run this with by displaying the time. So the top time is the times computed, and the bottom time is the time seen, given the fact that light takes a while to travel. So the bottom number is what Bob would see of Alice's time if he had a big telescope, and he could see a big clock on her spaceship. And this number is what Alice would see looking back toward Bob. So let's start that off. Okay, so right here, Alice has completed half the trip. You see that her clock reads 3, Bob's clock reads 5. So Bob sees Alice's time, or computes Alice's time, is slower. Actually, what he sees is 1.67. We'll ignore that for the moment, but he computes that her clock would be at 3 years, and her clock is running slower. She would see his, well, we won't say what she sees. We're talking about Bob's viewpoint. And we can finish the trip. And at the end, her clock will move 6 and his is 10. When they meet, they will agree that that's the times that they have on their clocks. Okay, now let's look at it from Bob's point of view by using Alice's line of simultaneity. Let's back up. Alice's line of simultaneity is different than his. It's angled relative to her her x-axis. So let's move this animation forward a bit, and let's get it to the 3. Okay, well, okay, when she gets to 3, we have a point that is, she's changing her velocities instantaneously, which is not possible. So in theory, she would have two lines of simultaneity then, in an instant, in that particular instant. But in my software, it always decides to go for the next segment of the travel, so it's going to point off to the future. But anyway, at this point, when she gets to 3, this will read 1.8. So she will compute that Bob's clock is running 60% slower than hers. And if we were to move this forward, okay, now at this point, her clock reads 3. His clock is now 8.2. So there, by the time she gets here at 10, it will have traveled 1.8 years. She will have taken up 3 more years, and she'll compute his clock is still running 60% slower than hers. Okay, so when we look at a single inertial frame at a time, um, we can see that each of their clocks run slower than the others because they're measuring time using a different line of simultaneity. As I said, the point here is not to really go through the twins paradox, but just to show what you can do using the diagrams. The next thing I'll do is I'll change to 1G acceleration. And so it's exactly the same problem as before, except now you get to see it without the weird unphysical events in the middle. Let me play that again. So here you can see that instead of instantly transferring between two times, the line of simultaneity kind of speeds up along Bob's world line. Anyway, the thing is, it doesn't take any much more programming to get this case than it does to get the other case, the one with the straight lines. The straight line version is pretty common because it's just easier to draw with hand tools, but it's just as easy to do an accelerated version using gamma. We can also look at the whole thing from Alice's point of view. Let's see what that looks like, and her simultaneity. Here, let's see, we've got, let's display Alice's grid. As we can see, her world line is always a curve, and his is always a straight line, no matter which frame you're looking at from. And so her initial frame is changing every instant in time, although she has some constant velocity sections of the trip here. But other than that, they're changing, and the software is just computing for each instant independent of the others. So that's about all I'm going to go through with this particular diagram. Okay, now I'm going to go into Bell's paradox. Bell's paradox has two spaceships. There's the blue and the red, or the left and the right. Both spaceships take off at the same time, and they're accelerating at the same rate. They have a string attached to them. That string is attached at time 0, and it's detached at time 5 years relative to the rest observer. So let's see what that flight looks like. So the question here is, does the string break? The string appears to be the same length as measured by the rest observer, so that shouldn't be a problem. It shouldn't break, but the correct answer is it will break. And the explanation is that the space in between the two ships is increasing. As you go faster, things contract relative to the rest frame. So if this space is staying the same in the rest view, then it's got to be bigger in its own frame. So I thought, well, this is a great opportunity to use my program to see if that's true. So let's look at the situation. Let me just stop the animations, go back, and let's look at this relative to the left spaceship. And we'll have left spaceship's line of simultaneity, what it thinks of as happening at the same time. And we'll start it off. Okay, so what we see is, from the blue ship's point of view, the red ship is indeed getting further away. So that would say, oh yeah, okay, I can see that it's happening, the thread would break. But we have a problem here. And that is that it's this thick area. This is where the thread's attached. This is where the thread's detached. Attached, detached. So what we're saying is simultaneous is not a point that actually has the thread attached. So we're not really looking at the problem the right way. And this becomes more evident if we look at the point of view of the other ship. So let's start it off again. And okay. Now we see that the blue ship, from the red ship's point of view, the blue ship is actually getting closer. But also, the points that are simultaneous is a point before the thread is attached to the ship. So this makes no sense as far as trying to determine the length of the thread. So I thought, well, I don't quite understand the problem. So let me take a different approach. Let's go back to the rest observer. And what I'm going to do is I'm going to put a bunch of points that I will be points along the thread so I can watch them. They will all accelerate at the same rate. So I can see what happens to them. So in the rest frame, it all looks great. The distance between the points is exactly the same. And it would seem like the thread's not going to break. Now let's look at it from the point of view of the left spaceship. And when we keep the measurement along the line of simultaneity for the rest frame, you can see that the distance between points on the thread expand, and so the thread is stretching. And this model of view basically says that it looks at the length from the viewpoint of the attachment of the thread to the ship. So things that are attached are all attached at the same time, and they're moving through. They have the same tau value. For each one, if you look at their clock, they would all have exactly the same reading at every point on this and in this animation. And let's look at it from the other ship's point of view. And we see also again the thread is stretching. So this seems like a better model. I'm not a physicist, and I don't know if my explanation is very clear, but when I draw it this way, it makes sense that we're keeping the points of attachment consistent and we're measuring the length along that way. So it demonstrates it's a tool for exploring a problem, and I think it made it very clear to me that my first setup just made no sense at all. And so it helped looking at it this way. This makes more sense. Now for the bad news. You create a diagram in Gamma by writing a program. So you do have to learn a programming language. It's a fairly simple language, but it's still it's harder than just pushing some buttons and sliding some sliders. Now here's a partial example of a Gamma script. And this one defines an observer. The observer's world line basically moves at 80% the speed of light for 4 light years, and then turns around, comes back. So this is the classic twins paradox example that we've covered earlier. So from there we just add a grid and some axes. Grid and axes are commands. They have parameters, but I'm using all the default parameters because we basically going to display a grid relative to the rest observer and the axes relative to the rest observer. And then the final line, the world line observer, is going to draw the world line for the observer that's defined above. So let's see what that looks like. this is a variation of the previous program. All I've done here is just added the first statement display. It sets up an origin and a scale so that the diagram it gets you closer to the region of interest. Let's see what that looks like. And here's another variation. This one's an animated variation. So it's the same program as before. We've added an animation statement. It basically just signals that this will be animated. And then we select a variable to animate, variable t for time. Now, gamma contains some useful functions. So the d to t function basically takes a distance and converts it to a time. T stands for rest time. Tau stands for observer time. So in this case, we're going to the rest time. So the distance the observer is going to travel is 8 light years. And so when we get t, we'll know when that is, the observer has traveled 8 light years. And that'll be the end of the trip. And we're going to step at intervals of 0.1. The animation is 30 frames per second. And so you can pick the step factor to get whatever speed you want. Again, we display the grid, the axes, and the world line, and then we display an event. We place an event at time t, where the observer happens to be at that point. So to find out where the observer is going to be, we take the time and get the matching x value, so t to x. We take the time, give it the observer, it returns the matching x value for that. And then we create a coordinate xt there for the event, and that's going to display the, it's going to animate that event. So we'll move along the world line from start to finish. So let's see what that looks like. And the final example, we'll change the scale a bit and the origin because we need a little bit more space here. Everything else is pretty much the same. The last statement is added, which is the frame statement. The frame says take the problem that's been specified in the script here, which is all relative to the rest frame, and draw it relative to whatever frame is given in the frame command. In this case, the frame is whatever the observer's frame is at time t. So it will change as we move through t for the observer. So let's see what that looks like. Okay, so what I'm doing in putting out this video is I'm looking for reviewers. I'd like to have some other eyes on it to find out what works, what doesn't work, what could be improved, what might be missing. I'm not a physicist, so having actual physicists look at this might be able to, a physicist might have better ideas of what's missing and what could be improved. Any enhancements, so whatever's there works, but if we had this other feature, it could be even more useful. And this is an early version. It's going to have a lot, it's going to have bugs, but as you've seen already, there's a lot that works fine, or else I wouldn't have been able to do these examples. So if you have any interest, write to me at this address, gamma@fraxis.org. Thanks for watching.